Hello my dear students, welcome to Teacher at Home. Today class we are going to learn the 10th chapter Work and Energy. In the previous few chapters we have talked about ways of describing the motion of objects, cause of motion and gravitation, and the concept that help us to understand and interpret many natural phenomena. It is work, closely related to work and energy and power. In this chapter we shall study the concepts all all living beings need food. Living beings have to perform certain basic activities to survive. We call such activities as life process. Energy for this process comes from the food. We need energy for other activities like playing, singing, reading, writing, thinking, jumping, cycling, and running. Activities that are strenuous require more energy. Animals too get engaged in activities. For example, they may jump and run. They have to fight, move away from enemies, find food, and find a safe place to live. Also, we engage some animals to lift weight, carry loads, pull carts, or plow fields. All such activities require energy. Think of machines. Last, list the machines that you have come across. What do you need for their working? Why do some engines require fuel like petrol and diesel? Why do living beings and machines need energy? Work. What is work? There is a difference in the way we use the term work in day to day life and the way we use it in science. To make this point clear, let us consider a few examples. Not much work in spite of working hand. Kamal is preparing for examination. She spent a lot of time in studies. She reads books, draws diagrams, organizes her thoughts, collects question papers, attends classes, discuss problems with her friends, and perform experiments. She expends a lot of energy on these activities. In common parlance, she is working hard. All this hard work may involve very little work. If we go by the scientific definition of work, you are working hard to push a huge rock. Let us say the rock does not move despite all the effort. You may completely exhausted. However, you have not done any work on the rock as there is no displacement of the rock. You stand still for a few minutes with a heavy load on your head. You get tired. You have exerted yourself and have spent quite a bit of your energy. Are you doing work on the Lord? The way we understand the term work in science, work is not done. You climb up the step of the staircase and reach the second floor of the building just to see the landscape from there. You may even climb up a tall tree. If we apply the scientific definition, these activities involve a lot of work. In day to day life, we consider any useful physical or mental labor as work. Activities like playing in a field, talking with friends, humming tune, watching a movie, attending a function are sometimes not considered to be work. What constitutes work depends on the way we define it. We use and define the term work differently in science. To understand, let us do the following. Science conception of work. To understand the way we view work and define work from the point of view of science, let us consider some situations. Push a pebble lying on a surface. The pebble moved through a distance. You exerted force in the pebble and the pebble got displaced. In this situation, work is done. A girl pulls a trolley and the trolley moves through the distance. The girl has exerted a force on the trolley and it is displaced. Therefore, work is done. Lift a book through a height. To do this, you must apply a force. The book rises up. Therefore, is a force applied on the book and the book has moved. Hence, the work is done. A closer look at the above situation reveals that two conditions need to be satisfied for work to be done. Force should act on an object and the object must be displaced. If any one of the above conditions does not exist, work is not done. This is the way we view work in science. A bullock is pulling a cart. The cart moves. There is a force on the cart and the cart has moved up. Think of some situations from your daily life involving work. Work done by a constant force. How is work defined in science? To understand this, we shall first consider the case where the force is acting in the direction of displacement. Let a constant force F act on an object. Let the object be displaced through a distance. S is the direction of the force. Let W be the work done. We define work to be equal to the product of the force and displacement. Work done is equal to force into displacement is equal to Fs. Thus, work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance moved in the direction of the force. Work has only magnitude and no direction. F is equal to 1 Newton and S equal to 1 m. Then the work done by the force will be 1 Newton meter. Here the unit of work is Newton meter or joule. 1 joule is the amount of the work done on an object when a force of 1 Newton displaces it by 1 meter along the line of action of the force. Look at the equation carefully. What is the work done when the force on the object is 0? What would be the work done when the displacement of the object is 0? Refer to the condition that are to be satisfied to say that work is done. A force of 5 Newton is acting on an object. Object is displaced through 2 meter in the direction of the force. The force acts on an object all through the displacement, then work done 5 Newton into 2 meter is equal to 10 Newton meter or 10 joule. Consider another situation in which the force and the displacement are in the same direction. A baby pulling a toy car parallel to the ground as shown here. The baby has exerted a force in the direction of displacement of the car. In this situation, the work done will be equal to the product of the force and displacement. Such situation, the work done by the force is taken as positive. Consider a situation in which an object is moving with a uniform velocity along a particular direction. Now a retarding force F is applied in the opposite direction. That is, the angle between the two directions is 180 degree. Let the object stop after a displacement S. In such a situation, the work done by the force F is taken as negative and denoted by the minus sign. The work done by the force F into minus S or minus F into S. It is clear from the above discussion that the work done by a force can be either positive or negative. Work done is negative when the force acts opposite to the direction of the displacement. Work done is positive when the force is in the direction of displacement. Example: a porter lifts a luggage of 15 kg from the ground and put it on his head 1.5 meter above the ground. Calculate the work done by him on the luggage. Mass of a luggage m is equal to 15 kg. Displacement s equal to 1.5 meter. Work done W is equal to F into S milligram into second. 15 kg into 10 meter per second into 1.5 meter. 225 kilogram meter per second. That's equal to 225 Newton meter is equal to 225 joule. Energy. Life is impossible without energy. The demand for energy is ever increasing. Where do we get energy from? The sun is the biggest natural source of energy to us. Many of our energy sources are derived from the sun. We also get energy from the nuclei of atoms, interior of earth and the tides. A few sources of energy are listed above. There are many other sources of energy. Discuss in small group how certain sources of energy are due to the sun. The work energy is very often used in our daily life. But in science, we get a definite and precise meaning. Let us consider the following examples. When a fast-moving cricket ball hits a stationary wicket, the wicket is thrown away. Similarly, an object when raised to a certain height gets the capability to do work. You must have seen when a raised hammer falls on a nail placed on a piece of wood. It derives the nail in the wood. We have also observed children winding a toy, such a toy car, and when the toy is placed on the floor, it starts moving. When a balloon is filled with air and we press it, we notice a change in its shape. As long as we press it gently, it can come back to the original shape when the force is withdrawn. However, if we press the balloon hard, it can even explode, producing a blasting sound. In all these examples, the object acquires through different means the capability of doing work. An object having a capability to do work is said to possess energy. Object which does the work loses energy, and the object on which the work is done gains energy. How does an object with energy do work? An object that possesses energy can exert a force on another object. When this happens, energy is transferred from the former to the later. Second object may move as it receives energy and therefore do some work. Thus, the first object have a capacity to do work. This implies that any object that possesses energy can do work. Energy possessed by an object is thus measured in terms of the capacity of doing work. Unit of energy is therefore the same as the act of work, that is joule. 1 joule is the energy required to do 1 joule of work. Sometimes a larger unit of energy called kilojoule is used. 1 kilojoule equal to 1000 joule. Form of energy. Luckily, the world we live in provides energy in many different forms. Various forms include mechanical energy, potential energy plus kinetic energy, heat energy, chemical energy, electrical energy, and light energy. James Prescott Joule was an outstanding British physicist. He is best known for his research on electricity and thermodynamics. Amongst other things, he formulated a law for the heating effect of electric current. He also verified experimentally the law of observation of energy and discovered the value of the mechanical equivalent of heat. Unit of energy and work called joule is named after him. Take a heavy ball, drop it on a thick bed of sand. A wet bed of sand would be better. Drop the ball on the sand bed from height of about 25 cm. This ball creates a depression. Repeat this activity from the heights of 50 cm, 1 meter, 1.5 meter. Ensure that all the depressions are distinctly visible. Mark the depressions to indicate the height from which the ball was dropped. Compare their depth. Which one is the deepest and which one is shallowest. Set up the apparatus as shown. Place a wooden block of non-mass in front of the trolley at a convenient distance. Place a non-mass of the pan so that the trolley starts moving. The trolley moves forward and hits the wooden block. Fix a stop on the table in such a manner that the trolley stops after hitting the block. The block gets displaced. Note down the displacement of the block. This means work is done on the block by the trolley as the block has gained energy. In this activity, the moving trolley does work and hence it possesses energy. A moving object can do work. An object moving faster can do more work than an identical object moving relatively slow. A moving bullet, blowing wind, a rotating wheel, a speeding stone can do work. How does a bullet pierce a target? How does the wind move the blades of the windmill? Object in motion possesses energy. We call this energy as kinetic energy. A falling coconut, a speeding car, a rolling stone, a flying aircraft, flowing water, blowing wind, a running athlete, etc. possess kinetic energy. In short, kinetic energy is the energy possessed by an object due to its motion. The kinetic energy of an object increases with its speed. How much energy is possessed by a moving body by virtue of its motion? By definition, we say that the kinetic energy of a body moving with a certain velocity is equal to the work done on it, making it acquire that velocity. Let us now express the kinetic energy of an object in the form of an equation. Consider an object of mass m moving with a uniform velocity u. Let it now be displaced through a distance s with a constant force F act on its direction of displacement. From the work done, W is Fs. The work done on the object will cause a change in its velocity. Let its velocity change from u to v. Let A be the acceleration produced. We studied three equations of motion. The relation connecting the initial velocity u and the final velocity v of an object moving with a uniform acceleration a and the displacement s, that is v square minus u square is equal to 2as. This gives s equal to v square minus u square by 2a. F equal to ma. Using the equation, we have w is equal to ma into v square minus u square by 2a, or w is equal to 1 by 2 m into v square minus u square. If the object is starting from the stationary position, U is equal to 0, then W equal to half mv square. It is clear from the work done is equal to change in kinetic energy of an object. If U equal to 0, work done will be half mv square. Thus, the kinetic energy possessed by an object of mass m moving with a uniform velocity v is E equal to half mv square. An object of mass 15 kg is moving with a uniform velocity of 4 meter per second. What is the kinetic energy possessed by the object? Mass of an object m is equal to 15 kg. Velocity is equal to 4 meter per second. E is equal to half mv square. That is equal to half into 15 kg into 4 meter per second into 4 meter per second is equal to 120 joule. Kinetic energy of the object is 120 joule. What is the work to be done to increase the velocity of a car from 30 km height per hour to 60 km per hour if the mass of the car is 1500 kg? Mass of a car m is equal to 1500 kg. Initial velocity u is equal to 30 km per hour, 30 into 1000 by 60 into 60 second, that is equal to 25 by 3 meter per second. Similarly, the final velocity is v equal to 60 km per hour, that is 50 by 3 meter per second. Therefore, the initial kinetic energy of the car E is equal to half mu square, half into 1500 kilogram into 25 by 3 meter per second. That is 15,000, 1,56,250 by 3 joule. The kinetic energy of a car is equal to 6,25,000 by 3 joule. As the work done is equal to change in kinetic energy is equal to 15,000. It is equal to 1,56,250 joule. Potential energy. Activity. Take a rubber band, hold it at one end and pull it from the other. The band stretches, release the band at one of the ends. Band will tend to retain its original length. Obviously, the band had acquired energy in a stretched position. How did it acquire energy when stretched? Take a slingy as shown below. Ask a friend to hold one of its ends. You hold the other end and move away from your friend. Now you release the slingy. Take a toy car, wind it using its key. Place the car on the ground. Did it move? From where did it acquire energy? Does the energy acquired depend upon the number of windings? How can you test this? Lift an object through a certain height. The object can now do work. It begins to fall when released. This implies that it has acquired some energy. If raised to a greater height, it can do more work and hence possess more energy. From where did it get the energy? Think and discuss. In the above situations, the energy gets stored due to the work done on the object. The energy transferred to an object is stored as potential energy if it is not used to cause a change in the velocity or speed of the object. You transfer energy when you stretch a rubber band. Energy transferred to the band is its potential energy. You do work while winding the key to a toy car. Energy transferred to the spring inside is stored as potential energy. Potential energy possessed by the object is the energy present in its virtue of the position of configuration. Take a bamboo stick and make a bow as shown. Place an arrow made of a light stick on it with one end supported by the stretched string. Now stretch the string and release the arrow. Notice the arrow flying off the bow. Notice the change in the shape of the bow. The potential energy stored in the bow due to the change of shape is thus used in the form of kinetic energy in throwing of the arrow. Potential energy of an object at a height. An object increases its energy when raised through a height. This is because the work is done on it against gravity while it is being raised. The energy present in such an object is its gravitational potential energy. Gravitational potential energy of an object at a point above the ground is defined as the work done in raising it from the ground to the point against gravity. It is easy to arrive at an expression for the gravitational potential energy of an object at a height. Consider an object of mass m. Let it be raised through a height h from the ground. A force is required to do this. The maximum force required to raise the object is equal to the weight of the object mg. Object gains energy equal to the work done on it. Let the work done of the object against gravity be W, that is work done. W is equal to force into displacement. Mg into h is equal to mgh. Since work done on object is equal to mgh and energy equal to mgh unit is gained by the object. This is the potential energy of the object. Potential energy of an object is at a height depends on the ground level or the zero level you choose. An object is given position can have a certain potential energy with respect to one level and a different value of potential energy with respect to another level. It is useful to note that the work done by gravity depends on the difference in vertical heights of the initial and final positions of the object and not on the path along which the object is moved. It shows a case where a block is raised from position A to B by taking two different paths. Let the height AB equal to h. In both the situations, the work done on object is mgh. Find the energy possessed by an object of mass 10 kg when it is a height of 6 meter above the ground. Given g is equal to 6.8 meter per second. Solution: mass of an object m is equal to 10 kg. Displacement h is equal to 6 meter. Acceleration due to gravity g is equal to 9.8 meter per second. Potential energy mgh 10 kg into 9.8 meter per second into 6, that is 588 joule. Potential energy is 588 joule. An object of mass 12 kg is at a certain height above the ground. If the potential energy of an object is 480 joule, find the length height at which the ground object is with respect to the ground. G is equal to 10 meter per second. Mass of an object m is equal to 12 kg. Potential energy E is equal to 480 joule. EP equal to mgh. 480 joule is equal to 12 kg into 10 meter per second into height. That height is equal to 480 joule by 120 kilogram meter per second is equal to 4 meter. Object is at a height of 4 meter. Can we convert? Are various energy forms interconvertible? Can we convert energy from one form to the another? We find in nature a number of instances to conversion of energy from one form to another. Many of the human activities and the gadgets we use involve conversion of energy from one form to another. Make a list of such activities and gadgets. Identify in each activity gadget the kind of energy conversion that take place. Law of conservation of energy in activity 10.13 and 10.14, we learned that form of energy can be changed from one form to another. What happened to the total energy of a system during or after the process? Whenever energy gets transformed, the total energy remains unchanged. This is a law of conservation of energy. According to this law, energy can only be converted from one form to another. It can neither be created nor destroyed. The total energy before and after the transformation remain the same. Law of conservation of energy is valid in all situations and for all kinds of transformation. Consider a simple example. Let an object of mass m be made to fall freely from a height h. At the start, the potential energy mgh and kinetic energy is 0. Why is the kinetic energy 0? It is 0 because its velocity is 0. Total energy of the object is thus mgh. As it falls, potential energy will change into kinetic energy. If v is the velocity of the object at a given instant, the kinetic energy would be half mv square. As the fall of the object continues, the potential energy would decrease while the kinetic energy would increase. When the object is about to reach the ground, h is equal to 0 and v will be the highest. Therefore, the kinetic energy would be the largest and potential energy will be the least. However, the sum of the potential energy and kinetic energy of the object would be the same at all points. That is, potential energy plus kinetic energy is equal to a constant, or mgh plus half mv square is equal to a constant. Sum of the kinetic energy and potential energy of an object is its total mechanical energy. We find that during the free fall of an object, the decrease in potential energy at any point in its path appears to an equal amount of increase in kinetic energy. There is thus a continual transformation of gravitational potential energy into kinetic energy. Rate of doing work. Do all of us work at the same rate? Do machines consume the transfer energy at the same rate? Agents that transfer energy do work at different rate. Consider two children A and B. Let us say they weigh the same. Both start climbing up the rope separately. Both reach a height of 8 meters. Let us say A take 15 seconds while B take 20 seconds to accomplish the task. What is the work done by each? The work done is the same, however, A has taken less time than B to do the work. Who has done more work in the given time, say 1 second? A stronger person may do certain work in relatively less time. A more powerful vehicle would complete a journey in a short time than a less powerful one. We talk of the power of machines like motorbikes and motorcar. The speed with which the vehicles change energy to do work is the basis of their classification. Power measures the speed of work done. That is, how fast or slow work is done. Power is defined as the rate of doing work or the rate of transfer of energy. If an agent does a work W in time T, then power is given as power equal to work by time, that is W by T. Unit of power is watt, in honor of James Watt, having the symbol W. 1 watt is the power of an agent, which does work at the rate of 1 joule per second. We can also say that power is 1 joule, 1 watt when the rate of consumption of energy is 1 joule per second. 1 watt is equal to 1 joule per second, or 1 watt is equal to 1 joule per second. Express the larger rate of energy transfer in kilowatt. 1 kilowatt equal to 1000 watt. 1 kilowatt is equal to 1000 joule per second. The power of an agent may vary with time. This means an agent may be doing work at different rate at different interval of time. Therefore, the concept of average power is useful. We obtain average power by dividing the total energy consumed by the total time taken. Two girls, each of weight 400 Newton, climb up a rope through a height of 8 meter. We name one of the girls A and the other B. Girl A take 20 seconds while B take 50 seconds to accomplish the task. What is the power expended by each girl? Power expended by girl A, weight of the girl mg equal to 400 Newton, displacement h is equal to 8 meter. Time taken equal to 20 seconds. Power P equal to work done by time taken mgh by t, 400 Newton into 8 meter by 20 seconds, 160 W. Watt. Power expended by girl B, weight of the girl mg equal to 400 Newton, displacement h equal to 8 meter, time equal to 50 seconds. Power equal to mgh by t, 400 Newton into 8 meter by 50 seconds is equal to 64 W. Power expended by girl A is 160 watt and that of B is 64 watt. A boy of mass 50 kg runs up a staircase of 45 steps in 9 seconds. The height of each step is 15 cm. What is power? G is equal to 10 meter per second. So weight of the boy mg is equal to 50 kg into 10 meter per second is equal to 500 Newton. Height of the staircase h is equal to 45 into 15 by 100 meter, 6.75 meter. Time taken to climb t equal to 9 seconds. From this, we get power equal to work done by time taken equal to mgh by t, 500 Newton into 6.75 meter, 9 seconds, 375 watt. Take a close look at the electric meter installed in your house. Observe its features closely. Take the reading of the meter each at 6:30 a.m. and 6:30 p.m. Do the activity for about a week. How many units are consumed during daytime? Units are consumed during nighttime, and tabulate the observation. So that's all about this chapter. If you are interested, please do like, share and subscribe my channel. Okay, thank you.